My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 584. In this lecture, I will continue my discussion on autoencoders in deep learning. Before understanding this lecture, I request all of you to go through my previous lecture, that is lecture number 583. This is the slide which is from lecture number 583. This model is called an autoencoder. This is simplest autoencoder with only one hidden layer. This is an input. Here you have an input layer, output layer, just one hidden layer, isn't it? Here I have my xi. Here I have xi dash. This is fully connected. This is also fully connected. These are activation units. This circles represents activation units, isn't it? The output I get here is xi dash, isn't it? The output that I get here of output layer is xi cap. I want my xi cap is very close to xi because I need to define loss function. What is the loss function for autoencoders? Logical loss function can be given xi, which is input, xi cap is the output, L of xi comma xi cap equal to norm 2 L2 norm of xi minus x cap whole square. I want this to be very small. If xi is exactly equal to xi cap, this loss function, this is sort of like distance between xi and xi cap. If the loss function is exactly equal 0, that is L equal 0. L equal 0, actually what is this L equal 0 means what? This is the property. This is the property that we want, isn't it? The ideal output, we want the loss to be 0. So this is like distance loss. You can think of this as distance loss. Now I have loss. Remember, this loss is differentiable. My loss is differentiable. This is simple neural network here with the input layer, isn't it? One hidden layer, one output layer. Of course, I have bunch of weights here. Just see, I have one input layer, one hidden layer, one output layer. I have bunch of weights here, w power 1. I have bunch of weights here, that is w power 2, isn't it? The fun part here, the most important fun part, I can create xi dash through this compression stage, isn't it? Just try to recall. I am creating representation of my points, isn't it? I am creating xi dash, isn't it? Your xi dash belongs to r power d dash, which is like compressed d dash dimensional representation of d. Your xi dash belongs to r power d dash, isn't it? So that this xi is d dimensional vector. Your xi belongs to r power d, while this xi dash is a d dash dimensional point. So I am able to compress this information of d dimensional vector into a d dash dimensional vector, and I am able to recreate the whole d dimensional vector from d dash dimensional vector. This is the simplest form of autoencoder. Very simple concept, and you have simple loss function. Of course, there are many loss functions. This is being L of xi comma xi cap equal to norm of xi minus xi cap whole square. One of the most used. And how do you train all of it? We will use machinery of optimizer algorithms like ADAM. We have all of that machinery, isn't it? Somewhere around 2010, when autoencoders become very popular, and there are some specialized forms of training algorithms called layer wise pre-training, which is very popular algorithm for training neural networks, not just autoencoders in the early 2010s, but right now everyone moved to advanced SGD algorithms like Adam. So this is the simple what we have seen right now is very simple. One hidden layer, isn't it? It is one hidden layer based autoencoder. Let's go to Wikipedia and see more complex variations of autoencoder. So instead of just one layer, why can't you have this? Why can't you have this? This is my input x. This is my output x cap, isn't it? Instead of x in Wikipedia's page they gave as x dash, but I am assuming as x dash, isn't it? Both of them are d-dimensional, means both x and x cap are of d-dimensional. Instead of one hidden layer, I can have more hidden layer. Just try to recall. Here I have only one hidden layer. In previous lecture we were discussing this one where we have only one hidden layer. Now I can have more than one hidden layers. Let's assume my d equal to, what is my d? D equal to, let me assume 100, isn't it? Of course d here is also I can first compress them into 50 dimensional point. Yes, which means you have 50 activation units. Output of the 50 activation units gives me 50 dimensional vector. I can do one more layer and get into 10 dimensions. Let me assume it's 10 dimensions. This is basically instead of one hidden layer neural network, here I have 3 hidden layers. Just see here how many hidden layers I have. 3 hidden layers. This is my input layer, isn't it? What is this? This is my output layer, isn't it? This is my layer 1, layer 2, layer 3. How many hidden layers do I have here? 3 hidden layers. And what we typically do is we compress as we go down. Just see here what's happening. I have 3 hidden layers. We compress as we go down, isn't it? Out of this is output of this is, what is the output of compression? Is xi dash, isn't it? So I am reducing dimensionality here and expanding dimensionality. Here reducing dimensionality, and on right side you are expanding dimensionality, isn't it? Just try to understand this particular diagram. This is my, I can say reducing dimensionality means I can say it is a compression stage, isn't it? And this is my expanding dimensionality means expansion stage to recreate. Why you are expanding? Expansion stage to recreate capital X itself. Very simple concept, and you can create a multi-layered autoencoders also. So you can have, just like multi-layer perceptron, you can have multi-layer perceptron based autoencoders, isn't it? Deep autoencoder basically means instead of one layer or 2 layers, you may have 5 or 6 or 10 layers. And of course, if you train any deep model, you apply all of your standard algorithms like dropout. You have to use all of the machinery anyway to train, because it is an optimization machinery. There are some variations to it. There is something called denoising autoencoder. This is a Wikipedia page on autoencoder. There is something like denoising autoencoder, which is very interesting idea. So let me explain what is denoising autoencoder is. Denoising autoencoder says this. Suppose if I am given a data set capital D of points x1, x2, so on xn. Let me say this is called this is actual data. Let me assume this is my actual data. let's assume that the data we get d tilde equal to x1 tilde, x2 tilde, x3 tilde, so on xn tilde. Let's assume this data is very noisy and corrupted. Now, if I want to achieve the true data, capital D, if I want to achieve the true data, capital D, this is like removing noise from data. One thing that people do here is, I have my noisy data here, d tilde. Let's build an autoencoder on top of the noisy data. I input the xi tilde into my autoencoder. What does an autoencoder returns to me? It returns xi dash, isn't it? Remember, all the points in capital D are d-dimensional. All the points x1, x2, so on xn belongs to r power d, that is d-dimensional vector. Now these points of xi tilde are also belongs to, these points are also belongs to d-dimensional vector. That's why x1 tilde, x2 tilde, x3 tilde, so on, this xn tilde also belongs to r power d. Now the representation that you get here, that is xi cap, that is, sorry, now the representation that you get here is xi dash. Your xi dash belongs to r power d dash, is more robust. It's a more robust, this is more robust to noise, isn't it? This must be more robust to noise, because whatever is the noise, what is an autoencoder is at trying to, what is an autoencoder is trying to achieve? It's trying to create smaller dimensional representation of data, isn't it? Autoencoder is trying to create a smaller dimensional representation of data, which means wherever it encounters noise or any corruption, isn't it? It's try to remove all of the data, isn't it? When people want to do denoise, when people want to do denoise data, what they do is this: they take xi in original data set and they convert into xi tilde if it is not available, isn't it? If it is not, people what they used to do, they take xi is original data set and they convert into xi tilde if it is not available, by just doing this xi plus some Gaussian noise, isn't it? By adding a Gaussian noise, isn't it? This xi is your original data. Xi is your original data. First step, they create noisy data points. Xi is original data points. Xi tilde is noisy data points. Sometimes if given noisy data points, no problem. You can take those noisy points like xi tilde equal to xi plus Gaussian noise, isn't it? You just train an autoencoder, and the representation that you get here, xi dash belongs to your xi. You will get xi dash is a very xi dash. You will get xi dash. Just say this one. What happens here? It's a data. Xi dash representation. Suppose, let's assume, let me explain like this. Let's assume we got capital D, and people want to come up with a robust representation, robust and noise-free representation. We need robust and noise-free representation, or noise-reduced representation. I can say it's a noise-reduced representation of points here. Then we intentionally add noise. Yes, isn't it? We intentionally add the noise. Your xi tilde equal to xi plus n of 0 comma sigma, isn't it? We are adding intentionally, we are adding noise. They take xi tilde and encode them through an autoencoder, and what you get here is your xi dash belongs to r power d dash, isn't it? Now, because you are intentionally added noise, the lower dimensional representation that you got, we will try to remove all of the noise and only learn robust noise-free representation of your data. There is something called sparse encoders. Sparse encoders are very interesting. There is something like sparse encoders. They are very interesting. So the next interesting concept is called sparse autoencoders. Sparse autoencoders are like this. Suppose you have an input. Let's assume this is input of very large dimensions. Let's assume your d equal to 10,000, like bag of words type of representation. Let me assume it is just like bag of words type of representation. Suppose, let's say I want to create 100 dimensional representation of this data. Let me assume I'm going to create 100 dimensional representation and it is fully connected again. I will get my d equal to 10k, isn't it? 10,000. Let's assume this is very simple autoencoder. Even I can have very deep autoencoders also. Now imagine if the output I am expecting here, the output I got here of the hidden layer, isn't it? I don't want to be dense, which means the 100 dimensional vector that I get here. What is the 100 dimensional vector here? This is 100 dimensional vector here. This could be dense, or if you observe this, I am expecting d is 100 dimensional. This xi cap don't want to be dense, isn't it? I don't want to be dense. That's why it's sparse encoder, isn't it? This could be your xi could be dense or sparse. That I don't care, but the output representation that I get here is here is my xi, here is my xi, here is my xi, this is my xi. I have also xi dash. Suppose my xi dash belongs to r power d dash. If I want this to be sparse, if I want this xi dash to be sparse, I can easily add that sparse auto encoder. This using L1 regularization. Let's not forget that fact. I have my standard loss. To loss, if I add L1 regularization, for loss I am adding L1 regularization. I need to add L1 regularization on the output of hidden layer, isn't it? I want as many of them as possible to be zero. That's what our L1 regularization, that's what our L1 regularization on L1 regularization on xi dash. So we have our loss function and L1 regularization. L1 regularization on the encoded values. What is encoded values here? Output of hidden layer. Output of hidden layer, isn't it? You can think of this as encoding stage. Which one is this is encoding stage? Yes, this is known as decoding stage or compression stage or compression stage or decompression stage. If you add L1 regularization on xi dash, and we know that L1 regularization L1 regularizer creates sparsity. L1 regularizer creates sparsity in the values. Just try to recall, we discussed that L1 regularization long back, isn't it? So there are multiple ways to create sparse autoencoder. One way is to do it through optimization. So there is one interesting relationship between autoencoder and PCA. If all of you, if all your activations are linear, and if you have a single sigmoid hidden layer, yes, if everything is linear and one sigmoid hidden layer, let's assume all of these units are, just try to recall, all of these units are sigmoid units. Just let me assume. Then the output you get of autoencoder, the output you get of autoencoder is very close related to principal component analysis. This is only when you have one hidden layer. But just I request all of you to refer this Wikipedia page. Also there is a page in towards data science on PC and autoencoder. I request all of you to go through this. This is the one this is only when you have one hidden layer, but when you have multiple hidden layers, no, it is not related to PCA. When you have only one hidden layer, it is related to PCA. When you have multiple hidden layer, it is not related to PCA. It is far more complex. Your autoencoder is far more complex than PCA. But if you just have one hidden layer and all of the activation units being sigmoid, the output that you get through autoencoder is very strongly related. It's very strongly related to PCA. And one of the things that we do a lot with autoencoder, in addition to dimensionality reduction, we can also use lower dimensions. Let's take our MNIST. Just see here, activation units are, of course, this we discussed. Let me take our MNIST data set that we saw long ago, that we keep reusing in deep learning a lot, where we have images of size 28 by 28, which means this data set has got 784 dimensions. Suppose each of these images, if I want representing 50 dimensional, if I want to represent this is a 50 dimensional vector, I think just use autoencoder to do dimensionality reduction on 784 dimensions while preserving the most of the information in 50 dimensional space. What I have here is basically a feature representation. What I have here is a feature 50 dimensional. I have here is 50 dimensional feature representation of your images. Autoencoder based dimensionality reduction is one of the most powerful dimensionality reduction algorithm. It is also very fast because it has all of the optimizers like Adam, all of the deep learning machinery that we are that we are simply just reusing and leveraging here, isn't it? So in addition to dimensionality reduction, autoencoders are also used for finding better I can say better feature representations of your data in an unsupervised fashion, because you don't have yi's here, you don't have labels here, you are just given xi's in your data set. So it is an unsupervised feature representation. It's a way to get features in an unsupervised fashion. Of course, any dimensionality reduction algorithm can do it, but autoencoder do job very well. I request all of you to go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.